I am Madhuchelvi, Associate Professor of Mathematics, Sri Sharada College for Women, Salem. In this session, let us discuss about the series of real numbers and its applications. Series of real numbers. First, let us see the definition of series. The infinite series, summation n equal to 1 to infinity an, is an ordered pair. Sequence an n equal to 1 to infinity, sequence sn n equal to 1 to infinity, where the sequence an n equal to 1 to infinity is a sequence of real numbers, and sn equal to a1 plus a2 plus and etc. plus an. The number an is called the nth term of the series. The number sn is called the nth partial sum of the series. Let us see an example. Consider 1 minus 1 plus 1 minus 1 plus 1, etc. Here Sn equal to 1 minus 1 plus 1 minus 1 up to minus 1 power n minus 1 into 1. Then this is equal to 1 if n is odd, equal to 0 if n is even. Sometimes it is convenient to index the terms of a series beginning with n equal to 0. In this case, summation n equal to 0 to infinity an and Sn equal to a0 plus a1 plus a2 plus and etc. an minus 1. Example, 1 plus x squared plus and etc. equal to summation n equal to 0 to infinity x power n. Next, let us see a definition of convergence of series. Let summation n equal to 1 to infinity an be a series of real numbers with the partial sums sn equal to a1 plus a2 plus and etc. plus an. N belongs to I. The series summation n equal to 1 to infinity an is said to converge to A if the sequence Sn n equal to 1 to infinity converges to A. So, the series is said to converge to a limit A if the sequence of partial sums converge to the limit A. Next, the definition of divergence. The series summation n equal to 1 to infinity an is said to diverge if the sequence Sn n equal to 1 to infinity diverges. That is, the sequence of its partial sums diverges. If summation n equal to 1 to infinity an converges to the limit a means the value of that summation n equal to 1 to infinity an is equal to a. Let us say a theorem. If summation n equal to 1 to infinity an converges to a and summation n equal to 1 to infinity bn converges to b, then summation n equal to 1 to infinity an plus bn converges to a plus b. Also, if C belongs to R, then the series summation n equal to 1 to infinity Can converges to Ca. Let us see the proof. Let Sn equal to A1 plus A2 etc. An. Tn equal to B1 plus B2 plus and etc. Bn. That is the partial sum of the series summation n equal to 1 to infinity Bn. Let Rn be the nth partial sum of summation n equal to 1 to infinity An plus Bn. Then how can we write that Rn? Rn equal to A1 plus B1 plus A2 plus B2 plus and etc. plus An plus Bn. These are all integers. So, we can write the commutativity, additive with respect to addition, the commutativity exists. That's why we can write it as A1 plus A2 plus and etc. plus An plus B1 plus B2 plus and etc. plus Bn. The first sum is Sn, second one is Tn. So, Sn plus Tn. Rn equal to Sn plus Tn. Since the series summation n equal to 1 to infinity an and the summation n equal to 1 to infinity bn converges to a and b respectively, limit n tends to infinity Sn equal to A and limit n tends to infinity Tn equal to B. By the theorem, if the sequence Sn n equal to 1 to infinity and sequence Tn n equal to 1 to infinity are sequences of real numbers and limit n tends to infinity Sn equal to L and limit n tends to infinity Tn equal to M, then limit n tends to infinity Sn plus Tn equal to L plus M. So by using the theorem, we can write here limit n tends to infinity Sn plus Tn equal to A plus B. That is, the nth partial sum of the series summation n equal to 1 to infinity an plus bn converges to A plus B. By the definition of convergence, the series summation n equal to 1 to infinity an plus bn also converges to A plus B. Next one, the scalar multiplication. Let C belongs to R and let Qn be the nth partial sum of the series summation n equal to 1 to infinity Can. So Qn equal to Ca1 plus Ca2 plus Ca3 plus and etc. plus Can. Let us take C outside, then C into A1 plus A2 plus and etc. An. That is equal to C into Sn. By the theorem, if the sequence Sn n equal to 1 to infinity is a sequence of real numbers and if C belongs to R, then limit n tends to infinity Sn equal to L and limit n tends to infinity Csn equal to Cl. By using that theorem, we can write here limit n tends to infinity Csn equal to Ca. That is the nth partial sum of the series summation n equal to 1 to infinity Can converges to Ca. Therefore, summation n equal to 1 to infinity Can equal to Ca. Next, we can see one theorem, that is the necessary condition for a series to be convergent. The condition is limit n tends to infinity an equal to 0. If the series is convergent, then the limit n tends to infinity an equal to 0. Proof, let summation n equal to 1 to infinity an equal to a and let Sn be the nth partial sum of the series summation n equal to 1 to infinity summation n equal to 1 to infinity an. By the definition, sequence Sn n equal to 1 to infinity converges to A. That is, limit n tends to infinity, Sn equal to A. Since if the sequence of real numbers sequence Sn n equal to 1 to infinity is convergent to L, then any subsequence of sequence Sn n equal to 1 to infinity is also convergent to L. That is, limit n tends to infinity, Sn minus 1 also equal to A. So, limit n tends to infinity, Sn minus 1 equal to A minus A, that is equal to 0. We know that Sn equal to A1 plus A2 plus n etc. An, Sn minus 1 equal to A1 plus A2 plus n etc. An minus 1. So, Sn minus 1 equal to An. This implies limit n tends to infinity an equal to 0. Now let us say an example. Consider the series summation n equal to 1 to infinity 1 by n is not convergent. But even though limit n tends to infinity 1 by n equal to 0. So, limit nth term of the series, if you give the limit n tends to infinity an equal to 0, but the series is not convergent. So, the condition is not sufficient. It is only necessary. For that only the above example is given. Next, we can see some problems on that series. Prove that if a1 plus a2 plus an etc. converges to S. Then a2 plus a3 plus an etc. converges to S minus a1. So in this problem, let us take Sn equal to a1 plus a2 plus an etc. plus an. Tn equal to a2 plus a3 plus an etc. plus an plus 1. Then we can write Tn as Sn minus a1 plus an plus 1. Since a1 plus a2 plus an etc. converges to yes, sequence Sn n equal to 1 to infinity converges to yes. Therefore, limit n tends to infinity Sn equal to yes. If summation n equal to 1 to infinity an is convergent, limit n tends to infinity an equal to limit n tends to infinity an plus 1 also equal to 0. Therefore, limit n tends to infinity Tn equal to limit n tends to infinity Sn minus a1 plus limit n tends to infinity an plus 1. That is, limit n tends to infinity Sn equal to S minus a1, but the limit n tends to infinity an plus 1 equal to 0. That's why we get limit n tends to infinity Tn equal to S minus a1. Therefore, the sequence of partial sums a2 plus a3 plus and etc. converges to S minus a1. Next problem, prove that the series summation n equal to 1 to infinity 1 by n into n plus 1 converges. Let us write first 1 by n into n plus 1 as 1 by n minus 1 by n plus 1. Then Sn equal to summation k equal to 1 to n 1 by k into k plus 1, that is equal to summation k equal to 1 to n 1 by k minus 1 by k plus 1. Then we can expand this series 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 plus an etc. plus 1 by n minus 1 by n plus 1. Then in middle terms all get cancelled. So we get only the first and last term, that is 1 minus 1 by n plus 1. So if you apply the limit both sides, we get limit n tends to infinity Sn equal to limit n 1 minus limit n tends to infinity 1 by n plus 1. That is 0. So 1 minus 0 equal to 1. Therefore, the sequence of partial sums converge to the limit 1 and hence the series is convergent. Next problem, for what values of x does the series 1 minus x plus 1 minus plus x minus x squared plus x minus x square minus x cube plus an etc. converges. For what values we have to find? First, let us take Sn. Sn of the above series. Sn equal to 1 minus x minus x squared plus x squared minus x cube plus an etc. x power n minus 1 minus x power n. That is equal to, as already we say, the middle terms getting cancelled, we get only 1 minus x power n. So if you apply the limit, both sides, limit n tends to infinity, Sn equal to 1 minus limit n tends to infinity x power n. Limit n tends to infinity x power n exists for x less than or equal to 1 only. Therefore, the series 1 minus x minus x squared plus an etc. converges if x is less than or equal to 1. So, for the answer is for what values it converges means if x less than or equal to 1, the series is convergent. Next problem, prove that for any a comma b belongs to R, the series a plus b plus a plus 2b plus a plus 3b plus etc. diverges unless a equal to b equal to 0. First, let us write an. What is the term an? An equal to a plus n minus 1 into B. If you apply the limit n tends to infinity an equal to a plus limit n tends to infinity n minus 1 into b. This is not equal to 0. This limit is not equal to 0 for a not equal to 0 and b not equal to 0. Therefore, the series diverges unless a equal to b equal to 0. Okay, yeah. Then the same for the same problem, another method is also there. Let us see that method. Sn equal to a plus b plus a plus 2b plus and etc. a plus n minus 1 into b. Limit n tends to infinity Sn equal to limit n tends to infinity a plus 2b, a plus b, a plus 2b, etc. Add everything. Then we get limit n tends to infinity a n times a. So na plus b 1 plus 2 plus 3 plus etc. n minus 1. Then limit n tends to infinity na plus b into the series, the binomial series. If you add, we get n minus 1 into n by 2. Then limit n tends to infinity n into a plus b into n minus 1 by 2 if you take n outside. Then this limit exists when a equal to b equal to 0. Therefore, the series diverges unless a equal to b equal to 0. Next problem is, show that summation k equal to 1 to infinity ak converges if and only if given epsilon greater than 0, there exists n belongs to I such that modulus of summation k equal to m plus 1 to n ak is less than epsilon for all m comma n greater than or equal to n. Then a sequence of real numbers, that is the solution is a sequence of real numbers sequence Sn n equal to 1 to infinity is said to be a Cauchy sequence. What is the definition? For any epsilon greater than 0, there exists n belongs to I such that modulus Sm minus Sn less than epsilon for all m comma n greater than or equal to n. So the sequence of summation n equal to 1 to infinity an converges if and only if the sequence Sn n equal to 1 to infinity of partial sums converges. The sequence Sn n equal to 1 to infinity is convergent if and only if it is a Cauchy sequence. If it is a Cauchy sequence only, we can get summation k equal to m plus 1 ak is less than epsilon. That is, if and only if for the given epsilon greater than 0, there exists n belongs to I such that modulus Sn minus Sm less than epsilon for all n greater than or equal, n comma m greater than or equal to n, if and only if, what is that? Modulus of a1 plus a2 plus n etc. plus an, that is Sn, plus an plus 1 am plus am plus 1 plus n etc. an minus of a1 plus a2 plus n etc. am. It should be less than epsilon for all n comma m greater than or equal to n. Then if you subtract the common terms, we get modulus of am plus 1 plus am plus 2 plus n etc. an is less than epsilon. That is, summation modulus of summation k equal to m plus 1 to n ak is less than epsilon. So that is the solution. We need the required solution. Then let us say the applications of a series. The application of series of real numbers appears in many areas of mathematics, science, and engineering. Let us see the areas. First one, solving the differential equations it is used. That is, the power series solutions help solve complex differential equations when standard methods don't work. Numerical methods. In numerical methods, series are used to approximate integrals, derivatives, and solution to equations numerically. Then in second, physics. In quantum mechanics, series represent wave functions and probabilities. In thermodynamics, they are used in partition functions and expansions like the viral expansion. In Fourier series, help express periodic functions in terms of sines and cosines, crucial in signal processing and vibrations. Then in engineering and signal processing, digital signal processing relies heavily on series expansions. Series help analyze filter behavior, frequency response, and signal reconstruction. In economics and finance, used in time series analysis for forecasting. Compound interest formulas and present or future value computations can involve geometric series. Then in computer science, algorithms for floating point arithmetic, cryptography, and machine learning may use approximations based on series. Recursive algorithms sometimes unfold into series. Then with this, we end this session. Thank you.